In the first week of July 2022, the images started arriving. NASA released the first deep-field photograph from the James Webb Space Telescope on July 11th, and within hours, the phones started ringing. Not the press phones, the ones on the desks of working cosmologists. Something was wrong with the picture. Not wrong in the way a blurry photograph is wrong. Wrong in the way a fossil record is wrong when it shows creatures that should not have existed yet. The image was too full, too detailed, too old. The photograph showed a galaxy cluster called SMACS 0723, and behind it, bent and stretched by gravity into arcs and smears of light, were hundreds of background galaxies reaching back billions of years. Astronomers had seen gravitational lensing before. They knew what the deep past was supposed to look like. Small, faint, chaotic, proto-galaxies in their infancy, barely assembled, featureless and dim. What Webb showed instead were galaxies that looked disturbingly mature. Bright, structured, enormous systems, sitting in an era of cosmic history when nothing like them was supposed to exist. Researchers who had spent decades building the models that predicted this region of time and space were looking at data that the models simply could not explain. Some initially assumed calibration errors, bad photometry, instrumental noise. Within days, it became clear the instruments were working perfectly. The data was the problem. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. The standard model of cosmology, the framework called lambda cold dark matter that had dominated the field since the late 1990s, had made specific predictions about what the early universe should look like. Not vague predictions, quantified ones, published ones, predictions that had survived every observational test for more than 20 years. James Webb was supposed to confirm them at a level of precision no prior telescope could reach. That was the mission. Instead, within the first weeks of data, researchers were quietly using a phrase that had never appeared in the literature before. Impossibly early galaxies. The word impossibly was not rhetorical, it was technical. These objects should not exist yet, according to the physics everyone had agreed on. And yet there they were, across multiple fields, flagged by multiple independent teams, at redshifts that placed them in the first few 100 million years of cosmic history. The crisis that followed has not resolved. It has deepened. This script will walk through what Webb actually found, why it breaks the standard picture, and what it might mean for the physics underneath everything we thought we understood about how the universe came to be. What they found was not the universe they had built their careers on. To understand why the data coming from James Webb is so disruptive, you have to understand what kind of machine you are actually dealing with. Start with the mirror. Hubble, the telescope most people picture when they think of space observatories, has a primary mirror 2.4 meters across. That is roughly the width of a large dining table. James Webb's primary mirror stretches to 6.5 meters. You cannot even build something that large as a single piece and fit it inside a rocket, so engineers designed it in segments, 18 hexagonal gold-coated beryllium panels that fold flat for launch and unfold in space like a mechanical flower opening in slow motion. The total collecting area is about 6 times what Hubble had. More collecting area means more light gathered, which means fainter objects become visible, which means you can reach further back in time. That last point matters enormously, and we will come back to it. The sunshield is the other thing people underestimate. It is the size of a tennis court. 5 layers of a material called kapton, each thinner than a human hair, stacked with vacuum gaps between them. On the sun-facing side, temperatures reach around 85 degrees Celsius. On the telescope side, it drops to roughly negative 233 degrees Celsius. That extreme cold is not incidental. It is required. James Webb observes in infrared light, and infrared is essentially heat radiation. If the telescope itself were warm, its own thermal glow would blind the detectors the way a flashlight blinds your eyes in a dark room. The sunshield keeps everything cold enough that the telescope can detect infrared signals from objects 13 billion light-years away without its own warmth getting in the way. Now, why infrared? This is the physics that makes everything else possible. The universe has been expanding since the Big Bang. When light travels across billions of light-years of expanding space, the expansion stretches the wavelength of that light. A photon that left a distant galaxy as visible light, maybe blue or ultraviolet, arrives at your detector with its wavelength stretched into the infrared range. The further away the source, the more the expansion has had time to stretch the light, and the redder it looks when it arrives. Astronomers call this redshift, and it is both a measurement tool and a problem. Hubble's detectors were optimized for visible and near-infrared wavelengths. The oldest, most distant galaxies, the ones from the first few 100 million years after the Big Bang, had their light stretch so far into the infrared that Hubble could barely see them, or could not see them at all. Webb's instruments are built specifically for mid and near infrared. That single design choice is what opens the first billion years of cosmic history to direct observation. The telescope orbits at a point called L2, the second Lagrange point, about 1.5 million kilometers from Earth in the direction away from the Sun. At L2, the gravitational pulls of Earth and the Sun combine in a way that keeps the telescope in a stable orbit, always facing away from both. This is important for 2 reasons. First, the sunshield can always block both the Sun and Earth's heat simultaneously. Second, the telescope is far enough from Earth that its own communications with ground stations are unaffected by terrestrial radio noise. The downside is that L2 is too far for astronauts to service it the way they serviced Hubble. Whatever Webb finds, it finds on its own. There are no repair missions. The sensitivity numbers are almost uncomfortable to read. Webb can detect objects roughly 100 times fainter than Hubble could at comparable wavelengths. In practical terms, that means a candle at the distance of the Moon is detectable. It means galaxies that were completely invisible before now appear clearly enough to measure their chemical compositions, their masses, their distances. This was the entire point. Scientists wanted to look back into the epoch of the very first galaxies, the so-called cosmic dawn, and see what was there. The standard cosmological model made specific, quantified predictions about what that era should look like. Small, faint, irregular clumps of gas slowly assembling the first stars. Nothing massive, nothing organized, nothing sophisticated. Those predictions had never been directly tested because no instrument existed that could look that far into the infrared with enough resolution and sensitivity to actually see objects from that period in any detail. Webb was built to test them. The mission was framed, at least in part, as a confirmation exercise. Send the best infrared telescope ever built to look at the exact epoch the Standard Model described in its most precise terms, and come back with the data that validates the picture. That meant JWST was not just a better telescope, it was a time machine aimed at the specific era where the Standard Model made its most confident predictions, and those predictions were about to have a very bad year. Before JWST started sending back images, cosmologists had a model they trusted, one that had survived every observational test for more than 2 decades. The model is called Lambda Cold Dark Matter, or Lambda CDM, and it is not a simple thing. It is a dense mathematical framework built over decades of observation, calculation, and revision, describing the full history of the universe from fractions of a second after the Big Bang to the present day. Lambda refers to the cosmological constant, Einstein's term for dark energy, the force apparently driving the universe's accelerating expansion. Cold dark matter refers to the invisible, slow-moving particles believed to make up roughly 85% of all the matter that exists. Together, these two components form the skeleton of the model. Everything else, every galaxy, every star, every planet, assembles on top of that skeleton. And for more than 20 years, Lambda CDM described the observable universe with extraordinary precision. To understand what JWST was expected to find, you need to understand what the model says the early universe looked like. In the beginning, matter was almost perfectly smooth. The Big Bang left behind a near-uniform soup of hydrogen and helium, with only the faintest, tiniest variations in density, ripples smaller than 1 part in 100,000. These were not nothing. Gravity works patiently. Regions that were even slightly denser than their surroundings pulled in more matter. Over millions of years, that extra pull accumulated. The denser patches grew denser still. What collapsed first, according to Lambda CDM, was not ordinary matter. It was dark matter. Dark matter doesn't interact with light. It doesn't get pushed around by radiation pressure the way hydrogen gas does. So while the early universe was still a hot, bright plasma hostile to ordinary matter clumping together, dark matter was already quietly falling inward, building structure in the dark. These dark matter concentrations are called halos. They are not sharp objects with surfaces. They are vast, diffuse clouds of invisible mass, held together by their own gravity, arranged in a web of filaments across cosmic space. The standard picture says small halos formed first, in enormous numbers, very early. Large halos came later, built by smaller ones merging together over time. This is called hierarchical structure formation. Galaxies were not supposed to appear fully formed. They were supposed to grow gradually, from the bottom up, with smaller systems assembling into progressively larger ones over hundreds of millions to billions of years. Ordinary matter follows the dark matter in. Hydrogen gas falls into these halos, drawn by gravity. Once inside, it has to cool. Hot gas doesn't collapse easily. The thermal pressure fights against gravity, so the gas radiates energy, cools slowly, and sinks toward the center of the halo. Eventually it gets dense and cold enough to fragment. Those fragments collapse further. Stars begin to form. But this is not a fast process. Cooling takes time. The gas has to shed enormous amounts of energy before it's dense enough to trigger star formation. In the Standard Model, the first stars don't appear until somewhere between 100 and 300 million years after the Big Bang, and even then, only in small numbers, in small systems, scattered thinly across space. What the early universe should look like under Lambda CDM is pretty specific. You should see small, faint, irregular proto-galaxies, compact little knots of gas and newly forming stars, nothing organized, nothing massive. The very first galaxies should be chemically primitive, almost pure hydrogen and helium, because heavier elements don't exist yet. Carbon, oxygen, nitrogen, iron, all of that gets made inside stars. The first galaxies haven't had time to make it. They haven't had time to cycle through generations of stellar birth and death. The universe at redshift 11 or 12 should look rough, chaotic, and young. Faint smudges, no grand spirals, no enormous masses, no signs of chemical complexity. The timeline implied by Lambda CDM is not vague. Researchers who built models based on this framework made concrete, quantitative forecasts about what JWST would see at different distances, and therefore different cosmic ages. They predicted luminosity functions, essentially how many galaxies of what brightness should exist at each epoch. They predicted mass distributions. They predicted what fraction of material should have converted into stars at what point in history. These were not rough guesses. They were published forecasts, specific enough to test, based on a model that had already successfully described the large-scale structure of the nearby universe, the distribution of galaxies across cosmic time within reach of earlier telescopes, and the precise patterns in the cosmic microwave background, the faint afterglow of the early universe that maps those original tiny density fluctuations. Lambda CDM wasn't just plausible, it was tested. The cosmic microwave background data from the Planck satellite fit the model's predictions to extraordinary precision. The distribution of galaxy clusters, the patterns of cosmic structure on large scales, the ratio of hydrogen to helium produced in the first minutes after the Big Bang, all of it aligned. Cosmologists had reasons to be confident. They weren't guessing at what JWST would find. They were expecting confirmation. The model worked beautifully for everything astronomers could see before Webb launched. The problem was what Webb started seeing the moment it opened its eye. The first image released publicly from JWST arrived on July 11, 2022, and it showed a galaxy cluster called SMACS 0723. President Biden unveiled it at a White House briefing. The image covered a patch of sky roughly the size of a grain of sand held at arm's length, and inside that patch were thousands of galaxies. The foreground cluster sat about 4.6 billion light-years away. Behind it, stretched and warped into arcs by the cluster's gravity, were galaxies much farther out. This effect has a name. Astronomers call it gravitational lensing, and it works because mass bends light. A galaxy cluster massive enough acts like a natural telescope, magnifying and distorting the light of whatever sits behind it. Einstein predicted this would happen. Hubble confirmed it. What JWST added was resolution, a sharpness that made the lensed background galaxies visible in a way no instrument had ever managed before. The arcs in the SMACS 0723 image were not just beautiful, they were data. Each one was a window into a galaxy that might otherwise be too faint to detect, its light amplified by the cluster sitting in front of it across billions of years of empty space. For the public, the image was a spectacle. For astronomers, it was a working document, and they got to work immediately. Within days of the data becoming available, researchers were pulling apart the background galaxies in that single frame, running their brightness and color through photometric analysis to estimate their distances and ages. This is standard procedure. You measure how red-shifted the light is, meaning how much the expansion of the universe has stretched its wavelengths toward the red end of the spectrum, and from that, you can calculate how far back in time you are looking. The further the galaxy, the more the light has stretched, the older the source. It is a method astronomers have used for decades. What came back from SMACS 0723 was not what the method was supposed to return. Some of the background objects looked wrong, too bright for their apparent distances, too massive for their estimated ages. A few were flagged almost immediately as candidates for galaxies seen at redshifts that, under the standard model, should have contained nothing organized enough to produce that kind of light. The researchers who spotted them did what scientists do. They checked their work. Then they checked it again. They looked for calibration errors in the new instrument, for photometric mistakes in the pipeline, for contamination from nearby sources bleeding into the measurements. The checks came back clean. The numbers were holding. Within weeks, other teams were looking at early JWST data from other fields and finding similar objects. The SMACS 0723 image had not been a fluke of one particular pointing. Whatever was showing up in that first frame was appearing across multiple observations. The phrase that started circulating in research groups and conference hallways was blunt. Impossibly early galaxies. Not a formal term at that point. More of a shorthand for a category of object that the standard model had not reserved a slot for, appearing in a time window when they had no business being there. The atmosphere in those early months had a particular quality to it. Excitement was part of it. Genuine excitement. The kind that shows up when data does something unexpected. But sitting underneath that was something closer to unease, because the researchers who knew the standard model best were also the ones most aware of what these objects implied if the measurements turned out to be right. Conferences that fall had a different texture than usual. Presentations that would normally have generated polite questions were generating extended arguments. People were careful with their language in public, but less careful in the hallways. The word crisis was not being used yet, not officially. But the conversations were moving in that direction. The first line of defense was the instruments. JWST had just come online. Its calibration data was still being refined. Any new telescope carries some uncertainty in its early measurements, and it was reasonable, even responsible, to attribute anomalies to that uncertainty rather than to fundamental problems with the model. Some researchers were vocal about this. The objects flagged as impossibly early galaxies were probably just photometric redshifts gone wrong, an artifact of estimating distance from color rather than from precise spectroscopic measurement. Get the spectra, they said. Confirm the redshifts with real wavelength data. Then decide if there's a problem. Over the following months, the spectra came in. Spectroscopic confirmation is the gold standard in this kind of work. Instead of inferring a redshift from an object's color, you measure the actual wavelengths of specific known emission lines in its light and calculate exactly where it sits in cosmic history. One by one, the objects that had been flagged as candidates came back confirmed. The redshifts held. The early estimates had not been far off. The instruments were working correctly. The calibration was not the issue. The party line was that the surprises were manageable, that the model just needed minor adjustments. That line did not hold for long. Within the first year of observations, something started showing up in the data that nobody had a clean answer for. To understand what was wrong, you need to understand what redshift actually means when astronomers use it to describe a distant galaxy. Light travels at a fixed speed. When you observe a galaxy billions of light years away, the light you are seeing left that galaxy billions of years ago. But the universe has been expanding the entire time that light was crossing the gap between that galaxy and your telescope. As the universe stretches, it stretches the wavelengths of the light traveling through it. Visible light gets pulled toward the red end of the spectrum. The further the galaxy, the more the light has been stretched, and the higher the redshift number astronomers assign to it. A galaxy at redshift 1 is seen as it was roughly 8 billion years ago. A galaxy at redshift 10 is seen as it was when the universe was only a few 100 million years old. Redshift 11, redshift 12, redshift 14. At those numbers, you are not looking deep into space so much as you are looking backward in time, all the way to an era when the universe had barely started. JWST was built to see exactly that era. Its infrared sensitivity exists for precisely this reason. At extreme redshifts, ancient visible light has been stretched so far that it arrives at the telescope as infrared radiation. Webb could detect it. Hubble largely could not. The expectation, built from decades of modeling, was that when you pointed the telescope at redshifts above 10, you would find small, faint, irregular blobs, proto-galactic structures, the raw material of what would later become galaxies after hundreds of millions or billions more years of gradual assembly, tiny and dim and barely there. That is what the standard model of cosmology predicted with confidence. What the telescope found instead was not that. Galaxies at redshifts of 11, 12, 13, and 14 were not faint, irregular blobs. Some of them were massive, luminous, structured in ways that suggested they had already been building stars at a furious rate for an extended period. The universe at that stage was somewhere between 300 and 500 million years old, depending on the specific redshift in question. The total age of the universe is 13.8 billion years. These galaxies were appearing in the first 2 to 4% of all of cosmic history, and they were already grown. The problem with that is not subtle. Under the lambda cold dark matter model, the standard framework that has dominated cosmology since the late 1990s, galaxy formation is a slow, layered process. Dark matter halos have to form first. Ordinary matter falls in and cools over vast timescales. Gas clouds condense and collapse into the first stars. Those stars live and die. The next generation forms from the enriched remains. Over hundreds of millions of years, slowly and incrementally, a galaxy accumulates mass. The standard model is not vague about this timeline. It makes quantitative predictions. At redshift 11, you should not have anything with billions of solar masses in stars already assembled. The math does not allow it. There simply has not been enough time for the process to run. Researchers flagged this almost immediately. Papers appeared in the months after the first deep field data came back, written in the cautious language of science, but carrying obvious alarm underneath. Ivo Laber at Swinburne University of Technology was among the first to formally document the problem, describing candidate galaxies in the early JWST fields that appeared to contain more stellar mass than the Standard Model could plausibly produce at those redshifts. Other teams followed quickly, confirming that these were not isolated detections. The phrase that started circulating, first in conference talks, then in papers, then everywhere, was the impossibly early galaxy problem. It means exactly what it sounds like. These galaxies should not have been able to exist yet. The universe had not been running long enough to build them by any mechanism anyone had written into their models. Some researchers pushed back. The initial photometric redshift estimates were uncertain. Maybe the galaxies were not as far away as they appeared. Maybe there were calibration issues specific to a telescope that had only just begun operating. That is a reasonable scientific response. You do not throw out a working model because of preliminary data. But the follow-up observations kept coming. Spectroscopic confirmations nailed down the redshifts directly, removing the ambiguity. The masses were harder to pin down precisely, but even the conservative estimates were troubling. A galaxy containing 10 billion solar masses in stars, existing within the first 500 million years, sitting in a universe that should have barely started forming its first scattered protogalactic structures, presents a categorical violation of the expected timeline, not a marginal one. The logical squeeze is this. If the universe is 13.8 billion years old, and some of these galaxies appear at an age of 300 to 500 million years, they had roughly 1/50th of all available cosmic time to reach the sizes Webb was observing. Under Standard Models, the process of building even a modest galaxy through normal gravitational assembly takes longer than that. To build something as massive as what Webb was recording in that era would require star formation running at efficiencies the Standard Model does not allow, starting almost immediately after the Big Bang, with no slow build-up phase, no gradual accumulation of the dark matter scaffold that everything else is supposed to hang on. Multiple independent teams working on different fields, using different analysis methods, were reaching the same uncomfortable conclusion. This was not a small discrepancy sitting at the edge of the error bars. It was a problem in the middle of the data, in multiple fields, confirmed by multiple teams, impossible to dismiss. The numbers themselves are worth sitting with, because they are the reason astronomers stopped trusting the old timeline. When JWST began returning confirmed spectroscopic data on galaxies from the earliest era of cosmic history, the figures attached to those objects did not fit. Galaxies seen just 500 to 700 million years after the Big Bang were coming back with stellar masses exceeding 10 billion times the mass of our Sun. Some were registering closer to 100 billion solar masses. For context, the Milky Way, a large, fully mature spiral galaxy that has been assembling itself for nearly 13 billion years, contains somewhere between 200 and 400 billion solar masses worth of stars. These early objects, caught when the universe was roughly 3 to 5% of its current age, were already approaching the same scale. That is not a small anomaly at the edge of the data. That is the data arriving with the wrong answers. To understand why those numbers are so disruptive, you have to understand what it actually takes to accumulate 10 billion solar masses in stellar form. Stars do not form from nothing. They condense out of cold molecular gas clouds, and that process takes time. A single star formation event inside one cloud of gas might run for tens of millions of years. After the most massive of those stars exhaust their fuel, they explode as supernovae, scattering newly forged heavy elements back into the surrounding gas and temporarily suppressing further star formation in that region. The gas has to cool again. New clouds have to collapse. The next generation of stars begins. Each cycle runs on timescales of hundreds of millions of years under standard conditions. Building 10 billion solar masses this W is not a single event. It is a long, interrupted sequence of events stacked on top of each other across enormous stretches of time. Think of it like constructing a city, not with a construction crew, but by waiting for towns to grow, merge, grow again, and merge again across centuries. You cannot rush the timeline by wanting the result sooner. The physics of gas cooling, gravitational collapse, and stellar feedback sets the pace. The Standard Model had those paces built in, tested against everything astronomers could observe before Webb launched. At redshift 10 or higher, corresponding to the universe being younger than 500 million years, that model predicted you would find the rough beginnings of structure. Small, faint, irregular blobs of gas and young stars, proto-galaxies, objects that might eventually grow into something recognizable, but at that point would look chaotic and dim, not yet organized into anything with a clear shape or a measurable billion solar mass stellar population. What JWST found instead were objects with defined morphologies, bright, compact, chemically enriched, sitting at redshifts of 11, 12, 13, and 14 with stellar masses that should not have had time to accumulate. One class of these objects carries masses exceeding 10 billion solar masses at a point when the universe was only around 330 to 400 million years old. The Standard Model's predicted upper limit for stellar mass at that epoch was orders of magnitude lower, not a factor of 2 off, not a rounding error. Some of these objects exceeded predictions by factors of 10 to 100. The comparison is worth making as plainly as possible. Before JWST, the most massive galaxy confirmed at redshift above 10 was a marginal detection, barely resolved, consistent with models. Within the first year of Webb operations, multiple teams were reporting candidates with masses that flatly contradicted those models. One study flagged 6 galaxies from the earliest observable epoch that appeared to have accumulated masses comparable to the Milky Way. The Milky Way is not young. It has had billions of years to pull in gas from its surroundings, merge with smaller galaxies, and convert generation after generation of stellar material into its current stellar population. The idea that something equivalent existed when the universe was a few 100 million years old had no place in the standard picture. There is a useful way to frame the scale of the mismatch. If you compress the entire 13.8 billion year history of the universe into a single calendar year, these galaxies formed before the middle of January. By that same calendar, the Milky Way did not finish assembling into a recognizable spiral until sometime in late summer. The Standard Model said that anything forming in early January should be small and primitive. What Webb found in early January was already enormous and organized. Some researchers initially pushed back on the mass estimates, arguing that photometric redshifts, measurements derived from color rather than direct spectroscopy, carry significant uncertainties and could be systematically biased toward higher masses. That is a legitimate concern. But as spectroscopic confirmations accumulated through 2023 and 2024, the masses held. The redshifts held. The objects were real. and they were where the photometry said they were. One candidate after another graduated from tentative detection to confirmed anomaly. The predicted universe at that epoch was supposed to be quiet and unformed. What showed up instead was something already built, already massive, already bright enough to be seen across more than 13 billion light-years of space. The numbers do not leave much room for interpretation. The Standard Model had no mechanism that could build something this large this fast. That gap between prediction and observation is where the crisis lives. One of the cleanest ways to express what JWST is finding is through a concept called star formation efficiency. The idea is straightforward. Any galaxy has a certain amount of raw material available, hydrogen mostly, along with helium, the basic baryonic matter that gravity has pulled together into one place. Star formation efficiency is simply the fraction of that material that actually ends up as stars. Not the gas floating around in the galaxy's outer atmosphere, not the material blown outward by stellar winds, just the stuff that collapsed all the way down and ignited into stars. In the modern universe, that number is somewhere between 10 and 20%. That means for every 10 units of available gas, a galaxy typically converts 1 or 2 into stars and leaves the rest as diffuse material, either suspended in the galaxy's halo or slowly drifting outward. 10 to 20% is already considered inefficient by naive gravitational standards. The question cosmologists have asked for years is not why galaxies convert so little, but why they convert so little when gravity, given enough time, should be able to drag almost everything down. The answer has to do with feedback. When massive stars form, they do not sit quietly. They radiate enormous amounts of ultraviolet light. They drive powerful stellar winds, and the largest of them, within a few million years, detonate as supernovae, sending shockwaves tearing through the surrounding gas. This is stellar feedback, and it is the mechanism that keeps galaxies from consuming themselves. The energy released by one generation of star formation heats the remaining gas, pushes it outward, and physically prevents it from collapsing into the next generation of stars. Without this break, a galaxy would convert its gas into stars far too quickly, burning through its fuel in a fraction of the time it actually takes. Feedback is not a minor correction. It is the central regulator of galaxy growth. The Standard Model of galaxy formation depends on it functioning reliably. Now look at what JWST is finding in the early universe. Researchers analyzing 6 of the earliest and most massive galaxy candidates observed by the telescope found something that, by the numbers, should not be physically possible. These galaxies appeared to have converted nearly all of their available gas into stars. Not 10%, not 20, nearly 100. When astronomers ran the mass budgets, the stars they could account for in these galaxies added up to essentially the entire baryonic mass budget those galaxies should have had available. There was almost nothing left over, no reservoir of unconverted gas, no sign of the material that feedback was supposed to preserve. This is not a small discrepancy. An efficiency of near 100% means the feedback mechanism either was not operating at all or was completely overwhelmed. It means the process that is supposed to regulate star formation in the Standard Model simply did not function the way it was supposed to in these systems. For that to happen, the physics of the early universe would have to differ from what we observe operating in every galaxy we can study in the modern universe. supernova explosions still happened. Radiation from massive stars still existed. The physics that drives feedback has not changed. Yet the outcome in these early galaxies looks nothing like the outcome feedback is supposed to produce. Some researchers have suggested the early universe's conditions might have made feedback less effective. Galaxies in the first few 100 million years after the Big Bang were denser, more compact, and filled with gas at higher pressures. Gas that is sufficiently dense can resist being driven outward by radiation and shock waves. The energy that would normally push material out of a less dense system might simply be absorbed and radiated away before it can do much damage to a compact, high-pressure gas cloud. That is one proposed explanation. But it is still a proposed explanation. It has not been demonstrated to account for efficiencies this extreme, and the degree to which it would need to suppress feedback to reach near total conversion is itself far outside what anyone modeled before JWST launched. An international research team led through the University of Geneva put the problem plainly when describing 3 ultramassive galaxies found within the first billion years of cosmic history, each nearly as large as the Milky Way. The star formation rates and stellar masses they were measuring required that these galaxies had been converting gas into stars at a pace and efficiency that current models simply could not accommodate. The phrase that kept appearing in the analysis was that the galaxies had used up nearly all available material, with almost no reservoir remaining. That is the signature of a system where the brake failed, or never existed in the first place. What makes this finding particularly hard to set aside is its specificity. This is not a vague sense that early galaxies were more active. These are measurements of stellar mass, estimates of total baryonic content, and a comparison between the two that produces a ratio no current model explains. 6 of the earliest and most massive candidates in the JWST catalogue appear to show the same thing. The numbers converge on the same conclusion from multiple independent analyses. Getting from 10 or 20% to nearly 100 requires that something in the early universe behaved in a way nobody predicted and nobody yet has a complete explanation for. In the same fields where the massive early galaxies were showing up, researchers noticed something else. Small, faint, red. Not the kind of red you get from glowing hydrogen or heated dust in a nearby star. Something deeper, more compact, and harder to explain. They started appearing in the early deep field images almost immediately, scattered across the background like embers in a photograph. Nobody knew what they were. That uncertainty has not fully resolved. The astronomical community has given them a name that reflects exactly how much remains unknown about them. They are called the little red dots, and they may represent the most genuinely mysterious objects JWST has yet catalogued. What they look like in the raw imaging data is deceptively simple. A point, smaller than the early massive galaxies, redder than almost anything else in the same field. In some images they appear barely distinguishable from noise, except that noise does not repeat with the same color signature across multiple independent observations. When researchers began stacking images from different JWST programs and comparing object catalogues, the same class of thing kept appearing. Compact, faint, red, and distributed throughout the deep fields at a frequency that quickly became impossible to write off as a calibration artifact. By the time systematic catalogues were assembled, hundreds had been identified. Some estimates now put the count in the thousands, when the full range of JWST Deep Field Program is included. The first question was what they actually are. There are two leading candidates, and neither one sits comfortably inside the standard model. The first is that they are extremely compact galaxies, small dense collections of stars with unusual stellar populations that skew their light toward red wavelengths in a way that does not match a straightforward redshift explanation. This would make them a genuinely new class of galaxy, unlike anything found in surveys of the nearby universe or in pre-Webb deep field imaging. Compact galaxies are not unheard of, but this compact, this red, this numerous, this far back, that combination does not fit any population astronomers were expecting. The second candidate is more unsettling. Many researchers looking at the spectral signatures of these objects have argued they are not primarily galaxies at all. They are active galactic nuclei, AGN, supermassive black holes consuming surrounding material at extreme rates, blazing so brightly that they outshine everything else in the galaxy around them. This is where the little red dots start to intersect with a much larger problem. If these objects are AGN, they represent supermassive black holes active and feeding at redshifts that push the black hole formation problem into even more extreme territory than the galaxy mass crisis alone implies. You can find a way, with considerable effort, to argue that the early massive galaxies might fall within a very generous interpretation of what the standard model can accommodate. AGN at these redshifts are harder to dismiss. Powering an AGN requires a black hole of significant mass already assembled, already at the center of a system, already accreting. Finding hundreds or thousands of them distributed across the observable sky at these distances means the black hole population in the early universe was far more developed than any reasonable version of the standard model allows. The red color itself became its own puzzle. Early analysis suggested that the redness of these objects was not entirely consistent with what you would expect from simple redshifted starlight. When light travels across an expanding universe, its wavelengths stretch. Ultraviolet light from a distant galaxy redshifts into the optical and infrared range. That process produces a specific signature, a predictable color gradient depending on the redshift. The little red dots were not matching those predictions cleanly. Their spectra showed excess redness in places that suggested something else was happening in addition to redshift. Dust was one possibility. Dense columns of dust inside or around the source could preferentially absorb shorter wavelengths, making the object appear redder than it says, Haud. This is known to happen in AGN, where a torus of gas and dust often surrounds the central black hole and filters the light emerging from the accretion disk. The dust hypothesis actually strengthened the AGN interpretation for some researchers because it provided a mechanism for the color anomaly that fit naturally with the black hole model. But the dust hypothesis created its own problems. Producing large amounts of dust requires dead stars. Dust forms in the ejecta of supernovae and in the winds of evolved giant stars. Getting enough dust to significantly redden the light from a system within the first few 100 million years of cosmic history means running through stellar generations fast enough to generate significant stellar death at an era when the first stars were barely getting started. If these objects contain that much dust, the star formation efficiency problem and the chemical enrichment problem both get worse, not better. The little red dots, regardless of which interpretation turns out to be correct, pull multiple existing anomalies toward each other. There is also a third possibility that gets less attention but has not been ruled out. Some researchers have argued that the little red dots might be a mixed population, some compact galaxies, some AGN, some objects where an active nucleus and an unusual stellar population are both contributing simultaneously, making spectral decomposition genuinely difficult. Distinguishing between these scenarios requires deep spectroscopy and obtaining sufficient signal from objects. This feint at this distance pushes even JWST close to its limits. The data is improving. New observations are narrowing the field. But as of the most recent published catalogues, no single explanation has achieved consensus across the community working on this problem. Whatever the little red dots are, they do not fit neatly into any existing category, and that alone is enough to keep a generation of astronomers occupied. The galaxy problem would have been enough on its own. Massive galaxies appearing billions of years too early. Organized and luminous and chemically enriched when the standard model says nothing like them should exist yet. That alone was enough to put the cosmological community on edge. But running underneath the galaxy problem, by some measures more severe, is a second crisis that the same JWST data exposed. It involves black holes. Specifically, it involves black holes that are far too large, in places they should not be. At times in cosmic history when they had no business existing. To understand why this is a problem, you need to understand how astronomers thought black holes were supposed to grow. The standard picture is straightforward. Massive stars, tens of times the mass of our Sun, burn through their fuel and collapse inward when they die. That collapse produces a stellar mass black hole, typically somewhere between 5 and 50 times the mass of our Sun. From there, the black hole grows slowly. It pulls in surrounding gas. It occasionally merges with other black holes when two of them wander close enough together. Over millions and then billions of years, through this steady accumulation, a black hole can grow from stellar mass up into the supermassive range, millions or billions of solar masses. Our own Milky Way has one of these sitting at its center. AS, supermassive black hole called Sagittarius A star, roughly 4 million times the mass of the Sun. By everything astronomers understood, getting from a 50 solar mass black hole to a 4 million solar mass one requires an enormous amount of time and an enormous amount of accumulated material. The universe is old enough to make that work today. The early universe was not. Here is what JWST started finding. Active supermassive black holes, not theoretical ones, not indirect hints, but actively feeding, luminous objects confirming their presence through the radiation they produce, sitting in galaxies that existed just a few 100 million years after the Big Bang. The numbers that come back from these observations are genuinely difficult to absorb. Some of these black holes appear to contain masses equivalent to hundreds of millions of solar masses, or more. The universe at that point was perhaps 300 or 400 million years old. Under the conventional growth model, there was simply not enough time to build something that massive from a stellar collapse. You would need to start with a seed black hole and feed it at the maximum theoretical rate. Cal led the Eddington limit continuously, without interruption, from the very first moments of the universe. Even then, the math is difficult. Some of the objects JWST has flagged are massive enough that even constant maximum rate feeding from the earliest possible starting point strains the arithmetic. One of the clearest examples is a galaxy astronomers have catalogued and informally labelled Virgil, observed as it appeared roughly 800 million years after the Big Bang. That sounds like a long time. In cosmic terms, it is the early afternoon of the first day. The galaxy hosting Virgil's black hole is not especially massive on its own. It is not one of the titans that broke the galaxy formation models, but the black hole inside it is consuming material at a rate dramatically out of proportion to the galaxy around it. In the modern universe, when astronomers observe supermassive black holes and their host galaxies, they tend to find a rough correspondence between the two. Bigger galaxies harbour bigger black holes. The two appear to grow together, each influencing the other's development through a feedback loop that astronomers have studied carefully for decades. In Virgil, that relationship is inverted. The black hole is not proportional to its host. It is consuming material faster than the galaxy around it should be able to supply. It exists at a scale that the host galaxy's mass does not explain. The black hole got there first, or grew faster. Either way, the expected ordering of events, galaxy forms, black hole grows inside it, has been reversed. That inversion is what makes this particular finding so troubling. It is not just that the black hole is large, it is that the relationship between the black hole and the galaxy surrounding it violates what the standard model predicts should be possible. The two are supposed to co-evolve. The evidence from Virgil, from a growing number of similar systems flagged in JWST data, suggests they do not always do that. In some cases, the black hole appears to run ahead of its host galaxy entirely. The theoretical responses to this have ranged from aggressive model revision to proposals that are further outside the mainstream. Some researchers have suggested that the first black holes in the universe were not formed by stellar collapse at all, but rather by the direct collapse of massive gas clouds, a process that would produce much heavier seed black holes to begin with. The subsequent accretion process, a head start. Others have proposed that early black holes grew faster than the Eddington limit is supposed to allow, feeding in short, intense bursts that standard physics does not easily accommodate. None of these explanations have achieved consensus. They are proposals for solving a problem that the data has confirmed is real. Marcia Rika, a Regents Professor of Astronomy and one of the architects of JWST's near-infrared camera, summarized the situation in terms that did not leave much room for ambiguity. It looks like the black holes actually get ahead of the galaxies in a lot of cases, she said. The expected sequence was galaxies first, black holes inside them second. What Webb is showing is that the sequence doesn't always hold. The phrase, "our ideas about how supermassive black holes formed were pretty much completely wrong," came from a researcher who has spent decades on this specific question. That gives you some sense of how far outside the expected result these numbers are. In early 2026, JWST handed cosmologists another data point they were not prepared for. The galaxy is called MOM-Z14. It was identified in April 2025, JWST, observing data, and announced to the wider community in early 2026, published in the Open Journal of Astrophysics. On the list of distant confirmed galaxies, it sits at the very top. The light reaching JWST from this object left its source just 280 million years after the Big Bang. To put that number in context, the universe is 13.8 billion years old. MOMZ14 is being seen at a moment when the universe had completed roughly 2% of its current age. Whatever is in that image, it is not supposed to look the way it looks. The distance alone would have been enough to generate headlines. But researchers working with the data quickly realized the distance was almost the least interesting part of the discovery. MOM-Z14 is brighter than models predict for any galaxy at that epoch. It is more compact than models predict. Its stars appear to have formed faster than any timeline in the standard framework allows. And then there is the chemical signature, which is the part that has proven hardest to explain away. When JWST's spectroscopic instruments analyzed the light from MOM-Z14, they found nitrogen. That single finding created an immediate problem because nitrogen does not come from the Big Bang. The universe at its origin produced hydrogen, helium, and trace amounts of lithium. Everything heavier than that is made inside stars. Carbon, oxygen, nitrogen. These elements are forged in stellar interiors through nuclear fusion, and they only get dispersed into space when stars die. A star lives, burns through its fuel, explodes or sheds its outer layers, and scatters enriched material back into the surrounding gas clouds. New stars then form from that enriched material. That is how heavier elements spread. That is the only way it works. Nitrogen specifically is what chemists call a secondary nucleosynthetic product. It cannot be produced in meaningful quantities during the first generation of stars. It requires stars to have already created carbon and oxygen through earlier fusion cycles, and nitrogen builds on those. The presence of nitrogen in a galaxy is a chemical fingerprint. It tells you the galaxy has already run through at least one complete cycle of star formation. Stars born, stars burned, stars dead, material scattered, new stars formed from what was left behind. One full generation. Minimum. At 280 million years after the Big Bang, there was barely time for a first generation. Standard models of stellar evolution place the lifespan of even the most massive, fastest burning stars at several million years. Then those stars die. Then the material they scatter must cool and collapse into new clouds. Then new stars must ignite. That sequence takes time even under the most optimistic assumptions. For MOM-Z14 to contain nitrogen at the age JWST is observing it, star formation would have had to begin almost immediately after the Big Bang and proceed at a pace that no existing model of early stellar physics comfortably accommodates. Rohan Naidu, a researcher at the MIT Kavli Institute for Astrophysics and Space Research and the lead author on the discovery paper, described the situation directly. With Webb, he said, "We are able to see farther than humans ever have before, and it looks nothing like what we predicted." That is not the language of a researcher describing a minor calibration surprise. That is someone describing a fundamental mismatch between expectation and observation. What makes MOM-Z14 sit differently from other early galaxy discoveries is the specificity of the problem. Massive early galaxies can theoretically be addressed by adjusting parameters in dark matter models, by invoking more efficient accretion pathways, by proposing that the initial mass function of early stars skewed toward heavier objects. These are uncomfortable adjustments, but they exist within the general architecture of the standard model. Chemistry is harder to negotiate with. The presence of nitrogen is not a matter of model tuning. It requires time. Not billions of years, but certainly more time than 280 million years comfortably provides, especially when you account for all the steps the synthesis chain requires before nitrogen can accumulate in detectable quantities. The discovery also adds weight to a pattern that was already accumulating in the JWST data. Massive early galaxies, supermassive black holes forming ahead of schedule, star formation efficiencies that break the standard feedback picture, and now a galaxy seen at the edge of the observable universe, enriched with elements that can only appear after stars have already been born and died in large numbers. Each of these findings is uncomfortable individually. Together, they describe an early universe that was running far faster, far hotter, and far more efficiently than the models ever suggested was possible. For nitrogen to be present 280 million years after the Big Bang, the galaxy had to have already lived through at least one complete generation of stellar birth, burning, and death, which is almost impossible to reconcile with any clock anyone has been using for how these processes are supposed to unfold. In January of 2026, a different kind of problem emerged from the data. Not a single galaxy behaving strangely. Not one anomalous object pushing against the edge of a model. This was a system, at least 5 galaxies, caught in the act of merging with each other. And it was doing this just 800 million years after the Big Bang. That is roughly 6% of the current age of the universe. The merger itself was startling enough. What the researchers found inside it made things considerably worse. To understand why this discovery hit the way it did, you need to think through what a galaxy merger actually requires. Before 2 galaxies can collide and begin combining, certain things have to be true. Each galaxy has to form independently. Each one has to accumulate enough mass to become gravitationally significant. They have to end up in the same region of space. Then they have to approach each other closely enough that their gravity begins pulling them together. That sequence takes time. In the modern universe, mergers happen because galaxies have had billions of years to form, drift, cluster, eventually encounter each other. The standard model assumes that in the earliest chapters of cosmic history, none of those conditions had been met yet. The universe was supposed to still be in the slow, uncertain business of assembling its first structures. 5 galaxies simultaneously interacting at 800 million years post-Big Bang says otherwise. The system was identified using JWST data and announced in early 2026. Researchers studying the images described what looked like an ongoing gravitational encounter. With the galaxies already deep into the interaction, their outer structures beginning to distort and blend. The fact that this was already happening so early forced an uncomfortable calculation. Each of those 5 galaxies had to have formed, grown massive, arrived at this location quickly enough to begin merging before the universe was even 1 billion years old. That is not just faster than predicted, it is faster than the model has any comfortable mechanism to explain. But the merger itself was not the most damaging part of the finding. What researchers found when they looked at the chemistry of the system was the detail that stopped people. The collision was redistributing heavy elements, oxygen among them, beyond the boundaries of the galaxies themselves. These elements were being scattered outward into the intergalactic space surrounding the merger through the gravitational violence of the interaction. That is a specific process called chemical enrichment of the intergalactic medium. In the standard model, it was not supposed to be happening at anything like this scale, this early. Here is why that matters. Oxygen does not come from the Big Bang. The early universe produced hydrogen, helium, and trace amounts of lithium. Everything heavier, carbon, nitrogen, oxygen, iron, was forged inside stars. For oxygen to exist inside these galaxies at 800 million years post-Big Bang, each of those galaxies had to have already cycled through at least one generation of massive stars. Stars that formed from primordial gas, burned hot, died in supernovae that scattered enriched material back into the galaxy. That enrichment cycle was supposed to take hundreds of millions of years at minimum. Now JWST was watching oxygen being flung beyond the galaxies entirely, into surrounding space, at an age when the first stellar generation should barely have finished. The team analyzing the data concluded that the redistribution was being driven primarily by the gravitational dynamics of the merger itself, rather than by galactic winds alone. That is an important distinction. Galactic winds, streams of gas blown outward by supernova pressure and radiation, are the usual mechanism by which enriched material spreads. But in this system, the gravitational shearing forces of 5 galaxies pulling at each other were stripping enriched gas directly from the galaxies and flinging it outward. This means that wherever galaxy mergers happened in the early universe, they may have chemically enriched their surroundings far faster and more efficiently than any model predicted. What this does to cosmological timelines is significant. The standard picture assumed that the early intergalactic medium was essentially pristine, hydrogen and helium, untouched by stellar processing, waiting patiently for the slow machinery of galaxy formation to eventually seed it with heavier elements. The quintet, as the system was nicknamed, suggests the seeding was already underway. Whatever the state of the intergalactic medium in the early universe actually was, it may have been considerably more chemically complex than any model running before JWST launched had anticipated. The discovery also offered a possible explanation for something researchers had noticed separately. JWST had already flagged the existence of massive but inactive galaxies at intermediate cosmic ages, large systems that had apparently exhausted their gas supply and stopped forming stars surprisingly early. If merger systems like the quintet burn through available gas at extraordinary speed during violent interactions, they could produce exactly that result, collapsing quickly into large quiescent structures with no fuel left. The timeline from quintet-type event to dead massive galaxy could be far shorter than anyone modelled. The most unsettling aspect was not the merger itself, it was how organised the system already looked, how structured and chemically mature at an age when struct. Ur was supposed to still be in its earliest chaotic phase. At some point in studying early universe galaxies, a researcher noticed something that stopped the conversation in its tracks. The galaxy in question had formed less than 2 billion years after the Big Bang. It was massive. It had already stopped producing new stars. And when researchers looked at its motion, they found almost nothing. No measurable rotation. A galaxy that large, that old in cosmic terms, sitting essentially still. To understand why that is so disorienting, you need to understand what rotation means for a galaxy and why every galaxy we have ever studied in the modern universe spins. When a cloud of gas collapses under gravity, it almost never falls perfectly inward from every direction equally. There is always some slight asymmetry, some net angular momentum inherited from the larger structure it formed within. As the cloud contracts, that angular momentum is conserved. The same physics that makes a spinning ice skater speed up when she pulls her arms inward applies here, just at a scale measured in light years. The collapsing gas spins faster and faster as it gathers inward, and the result is a rotating disk. Stars form inside that disk, and the rotation becomes locked into the galaxy's structure for billions of years. This is not a subtle effect. Rotation is one of the most fundamental signatures of how galaxies form. It gets more pronounced the younger you go. Older galaxies have had time for gravitational interactions with neighbors to complicate their rotation curves, for mergers to scramble angular momentum, for billions of years of dynamical evolution to soften the original spin. Young galaxies should not have had any of that. They should be spinning faster, not slower. The original angular momentum from their formation should still be present and relatively undisturbed. This is textbook physics. It is not a complicated prediction. It is simply what happens when matter falls together under gravity. The Magaz 3NE survey, which targeted some of the most massive known galaxies in the early universe, had already confirmed that this particular galaxy was extraordinary before the rotation data came in. It was carrying several times as many stars as the Milky Way. It had already gone quiet, meaning star formation had shut down completely, leaving behind an enormous passive system at an age when the universe was still in what most models would call early adolescence. That combination alone was alarming enough. Massive and already dead, at a cosmic age where the standard model barely expected galaxies to be getting started. Then came the rotation measurement. No spin, or close enough to none that no instrument could find it. Researchers tried to account for this. The most obvious possibility is that the galaxy had undergone so many mergers in rapid succession that the competing angular momenta from each collision had cancelled out. If you collide enough spinning objects from enough different directions, the net rotation can theoretically approach zero. But this creates its own problem. The kind of merger history required to strip a galaxy of all measurable rotation without tearing it apart entirely is extraordinarily specific. You need multiple collisions, each arriving from the right direction at the right time, adding up to near-perfect cancellation. The probability of that happening within the first 1 billion or 2 years of cosmic history, before the universe has even had time to build up the infrastructure of dense cluster environments where repeated mergers would be common, stretches the model close to its breaking point. There is another possibility that some researchers have considered. The galaxy may have formed through a process fundamentally different from the standard picture of gas cloud collapse. If matter in the early universe could assemble in ways that never involved a rotating disk to begin with, perhaps through direct collapse of extremely massive and relatively symmetric gas structures, then there would be no inherited rotation to preserve. But this requires early universe physics that operates very differently from what we observe in the modern cosmos, and proposing it creates more questions than it answers. What makes this finding land so hard is that it is not anomalous in the way a measurement error or a statistical outlier would be. A measurement error gives you a wrong number. This gave a clear answer. The answer was just the wrong one for everything we know about how gravity and angular momentum work together when matter gathers into structures. The galaxy is not spinning. It is massive. It stopped forming stars early. And it is sitting in a universe that was less than 2 billion years old when all of that had already happened. The quintet showed the universe could organize complex interacting systems faster than expected. This galaxy is a different kind of problem. It is not a question of speed. It is a question of whether the most basic mechanical outcome of gravitational collapse, the spin that every collapsing object in physics is expected to develop, was somehow bypassed entirely. A galaxy that formed less than 2 billion years after the Big Bang and shows no measurable rotation is either the product of processes we do not understand or evidence that some very basic assumptions about what drives galactic structure need to be rebuilt from the ground up. Bar structures in spiral galaxies are common in the modern universe. The Milky Way has one. Look at almost any image of a large spiral galaxy and you will likely see it. A thick, elongated band of stars running straight through the center, connecting the two sides of the disk like a bridge. About 2/3 of all large spiral galaxies in the modern universe carry one of these bars. They are so common that astronomers stopped finding them remarkable a long time ago. Then JWST found one where it had no business being. In February of 2026, a research team led by Daniel Ivanov at the University of Pittsburgh announced the discovery of a strong candidate for one of the earliest known barred spiral galaxies ever observed. The galaxy existed in the young universe, well within the first couple billion years after the Big Bang. On its own, a barred spiral galaxy sounds unremarkable. In that context, it is extraordinary. To understand why, you have to understand what actually has to happen inside a galaxy before a bar can form. A stellar bar is not something that just appears. It is a structure that emerges from a very specific set of physical conditions, all of which have to be present at the same time. First, the galaxy needs a substantial rotating disk. Not just any rotating mass of stars, but an organized, flat, spinning disk where stars are moving in roughly circular orbits around a common center. Building that kind of disk takes time. Gas has to cool, settle, and form stars over many generations. The disk has to stabilize. Second, the stellar density inside that disk has to be high enough to support what physicists call density wave perturbations. These are slight imbalances in the distribution of stars that, under the right conditions, can amplify into large-scale patterns. A bar is one of those patterns. Thin or sparse disks cannot sustain them. Third, the system has to be dynamically stable. A galaxy being torn apart by mergers or bombarded by infalling gas clumps cannot organize a clean bar pattern. The galaxy needs to have settled down enough that orderly orbital resonances can take hold. Fourth, time. The bar pattern itself needs time to develop and lock in. Orbital resonances build gradually. The elongated structure has to sweep up stars into coherent alignment through repeated gravitational nudges over many orbital cycles. Each of those conditions requires extended evolution, and in the standard model of galaxy formation, extended evolution is exactly what the early universe does not offer. The universe at a few 100 million to a couple billion years old is supposed to be chaotic. Gas is still falling in. Mergers are frequent and violent. Disks, where they exist at all, are expected to be turbulent and irregular. The first galaxies in the standard picture look nothing like the organized, rotationally supported structures that bars require. They are irregular blobs, chaotic assemblies of gas and young stars, nothing like the settled spiral galaxies of the modern universe. This is why the Ivanov discovery landed the way it did. The galaxy is not simply old, it is organized. It has a disk mature enough to support density waves. It has stellar density sufficient to lock those waves into a persistent bar pattern. It has the dynamical stability that a bar requires to exist and remain coherent over any meaningful stretch of time. All of that compressed into an age when the standard model says the building blocks of such organization should barely have arrived. The comparison to the non-rotating galaxy from the previous stretch of JWST findings is instructive here. Both discoveries are pointing at the same underlying strangeness from different angles. One galaxy shows no rotation when it should have abundant rotation. Another shows an organized bar structure when it should show chaotic disorder. They are mirror images of the same problem. Early galaxies behaving as if they have already lived through billions of years of quiet evolution that the timeline does not allow them. The gap between what Lambda CDM predicts for galactic structure at this epoch and what JWST is actually resolving in its images is not a subtle disagreement. It is a difference between a young universe full of rough, unfinished pieces and a young universe that already contains finished, refined structures. What makes bars particularly unambiguous as a diagnostic is that they are not a matter of interpretation. A bright, elongated structure running through the center of a galactic disk either exists or it does not. There is no version of a stellar bar that is partly formed. The structure either organized itself into coherence or it did not. And for it to organize, every preceding condition had to have been met. A rotating disk, stellar density, dynamical stability, time. You are not supposed to find a stable, organized bar in a galaxy that young. The data says otherwise. Among the stranger morphological findings from JWST is what the early galaxies actually look like. Not their mass, not their brightness, not how chemically mature they appear, but their shape. When researchers began cataloguing thousands of early universe galaxies across JWST's deep field images, they noticed that the distribution of shapes was off. Modern galaxies come in a range of forms: spirals, ellipticals, irregular blobs caught mid-merger. But there is a statistical distribution to that variety, and the early universe is not matching it. A significant fraction of the early galaxies Webb is pulling out of the data are elongated, stretched. They look less like the round or gently flattened systems astronomers expected, and more like ovals, rods, or smeared points of light. Some are compact enough to appear almost cigar-shaped. The effect is systematic enough that it shows up not in one field or one observing campaign, but across multiple datasets from different programs. Alvaro Pozo of the Donostia International Physics Center, working with Arizona State University's Rogier Windhorst, published an analysis in Nature Astronomy describing what this pattern might actually mean. Their conclusion pointed somewhere uncomfortable. The shapes of early galaxies might be telling us something about dark matter that current models are not equipped to handle. Dark matter is invisible. It emits no light, absorbs no light, and leaves no direct fingerprint on any detector. The way astronomers infer its presence and distribution is almost entirely indirect, through the gravitational effects it has on the visible matter around it. Galaxies form inside dark matter structures called halos, enormous gravitational wells where ordinary matter gradually accumulates, cools, and collapses into stars. The shape of a galaxy, the way its visible stars and gas are distributed, should broadly reflect the geometry of the dark matter halo surrounding it. A spherical halo tends to produce a rounder galaxy, A halo that is elongated or triaxial, meaning it has different extents along 3 separate axes, tends to produce a more stretched distribution of visible matter within it. This is not controversial physics. It follows directly from how gravitational collapse works. The dark matter scaffolding sets the geometry. The ordinary matter builds itself on that geometry. So when you see galaxies in the early universe that are systematically more elongated than expected, the straightforward reading is that the dark matter halos containing them were also more elongated than current models predict. The Lambda CDM framework has detailed predictions about halo shapes. Those predictions are derived from computer simulations of how dark matter structures evolve from the slight density fluctuations of the early universe. If the observed galaxy shapes don't match those predictions, either the simulations are wrong or the physics going into them is incomplete. There is a deeper possibility that Pozo and Windhorst's analysis raises. Dark matter's properties might not be constant across cosmic time. In the modern universe, the standard assumption is that dark matter is cold, meaning it moves slowly, and collisionless, meaning it barely interacts with anything except through gravity. Those 2 properties shape everything about how halos form and what they look like. But in the extreme density of the early universe, where matter was packed into a fraction of the volume it occupies today, there is no guarantee that a particle species behaving one way in the modern universe behaved the same way 13 billion years ago. If dark matter had different effective properties in the early universe, if it was warmer, or if it had some weak self-interaction that it effectively lost as the universe expanded and cooled, its HAL-OS would have formed with different geometries. You would expect exactly the kind of elongation JWST is finding. What makes this finding significant is not just that it adds another anomaly to the list. It is that the anomaly sits at the foundation of the whole structure. The galaxy mass problem, the black hole problem, the star formation efficiency problem, all of those involve ordinary matter behaving unexpectedly. This is different. This is a potential signal from the dark matter itself, from the invisible framework that was supposed to be well understood, even when everything built on top of it was surprising. The standard model is not agnostic about halo geometry. Simulations produce specific predictions, and those predictions can be tested. JWST is producing the test, and the early returns are not clean. It is worth noting that halo geometry is notoriously difficult to measure even indirectly. The connection between observed galaxy shape and underlying dark matter distribution involves assumptions that researchers are still stress testing. But the signal is consistent enough that dismissing it as noise requires explanation. Something is producing the elongation, whether that something is dark matter physics, a missing piece of early universe dynamics, or a systematic effect in how young galaxies assemble their stars. Nobody has a settled answer. Dark matter is supposed to be the invisible scaffolding that everything else is built on. And if the scaffolding was shaped differently in the early universe than current models predict, the question of what visible matter was actually built on becomes considerably more complicated. Before JWST even launched, there was already a problem with the expansion of the universe that cosmologists had been quietly arguing about for years. It did not have the drama of vanishing galaxies or missing black holes. It was subtler than that. It was a number that refused to stay the same, no matter how you measured it. The fact that nobody could explain the disagreement had been building into something serious long before Webb pointed its mirror at the sky. The number in question is called the Hubble constant. It describes how fast the universe is expanding, specifically, how many additional kilometers per second a galaxy picks up in its recession from us for every megaparsec of distance between that galaxy and Earth. A megaparsec is about 3.26 million light-years. The Hubble constant tells you the expansion rate right now. For decades, getting a precise value for it was considered one of the central goals of modern cosmology. By the 2000s, two independent methods had gotten precise enough to matter, and they disagreed. The first method starts with the oldest light in the universe, about 380,000 years after the Big Bang. The universe had cooled enough for electrons and protons to combine into neutral hydrogen for the first time. When that happened, light that had been trapped in a dense hot plasma was suddenly free to travel. It has been traveling ever since. We detect it today as a faint glow of microwave radiation coming from every direction in the sky, called the cosmic microwave background, or CMB. The pattern of temperature variations in the CMB encodes enormous amounts of information about the early universe. Cosmologists can work forward from that pattern to calculate what the expansion rate should be today. The answer they get is around 67 to 68 kilometers per second per megaparsec. The second method works in the opposite direction. Instead of starting in the distant past and calculating forward, you measure the expansion rate directly using objects in the nearby universe whose distances you can determine independently. The best tools for this are Cepheid variable stars that pulsate at a rate directly tied to their true brightness. Type 1, a supernovae, which explode at a consistent peak luminosity that can be seen across vast distances. By combining these so-called standard candles into a distance ladder, calibrating the nearer ones against each other and using the farther ones to push out to cosmological scales, astronomers measure an expansion rate of around 73 kilometers per second per megaparsec. The gap between 67 and 73 is roughly 5 to 10 kilometers per second per megaparsec, depending on which specific measurements you use. That sounds small. It is not small. The error bars on both measurements had shrunk tight enough by the mid-2000s that the two values should have overlapped if they were both correct. They did not overlap. They sat on opposite sides of a gap that was statistically significant enough that calling it a coincidence required contorting the math in uncomfortable ways. Cosmologists gave the problem a name. They called it the Hubble tension. The immediate hope was that the tension was instrumental. Hubble Space Telescope measurements of Cepheids drove much of the distance ladder work. If something subtle was off in how Hubble measured those stars, contamination from nearby stars, systematic calibration errors in crowded fields, that could shift the local measurement closer to the CMB value and dissolve the problem. This was a reasonable hypothesis. Hubble's resolution was good, but not perfect. The crowded stellar fields near Cepheids introduced real uncertainty. For years, some researchers held on to the expectation that better data would close the gap. Then, JWST began operating. In 2024, Webb turned its instruments toward the same Cepheid populations that Hubble had used to build the distance ladder. Webb sees in infrared with a mirror roughly 6 times the collecting area of Hubble's. Its resolution in crowded stellar fields is dramatically sharper. If background stars were contaminating Hubble's Cepheid measurements and inflating the apparent brightness of those stars, Webb would catch it. The analysis came back clean. Webb confirmed the Hubble-Cepheid distances. The local expansion rate did not move. It stayed near 73 kilometers per second per megaparsec, sitting right where the Hubble measurements had placed it, with tighter error bars than ever before. That was the moment the instrumental escape hatch closed. The tension was not a measurement artifact. Both instruments were working correctly. Both methods were producing reliable numbers. The numbers simply did not agree. No amount of reprocessing or recalibration was going to bring them together. What that leaves is a genuinely uncomfortable list of possibilities. Either the early universe was different from what the standard model describes, meaning the CMB-based calculation is built on assumptions that are subtly wrong about conditions in the first few 100,000 years after the Big Bang, or the physics of expansion in the modern universe is more complicated than general relativity predicts, meaning dark energy is not a simple cosmological constant, but something that changes over time. Pulling expansion in a direction the standard equations do not accommodate. Or both are wrong in different ways that happen to compound into a consistent-looking discrepancy. Some researchers have proposed early dark energy, a brief pulse of extra expansion driving energy in the young universe that would shift the CMB prediction upward. Others have suggested interactions between dark matter and dark energy that current models treat as non-existent. None of these proposals has yet achieved the kind of broad confirmation that would move it from hypothesis to accepted physics. What is certain is that the Hubble tension did not go away when JWST confirmed the measurement. It got harder to explain. When two completely independent methods of measuring the same number give different answers, and both instruments are confirmed to be working correctly. The obvious conclusion is that something about the universe itself is not behaving the way the model says it should. There is another layer to what MOM-Z14 revealed that does not get discussed as much as its distance. The distance record is the headline. But sitting underneath that headline, buried in the spectroscopic data, is something that in some ways is harder to explain than the distance itself. The galaxy contains nitrogen. That single fact, 4 words, carries implications that run directly into the foundations of how chemists and astrophysicists think the universe builds its periodic table. The early universe did not have a periodic table. Not really. In the minutes after the Big Bang, the only elements that existed in any meaningful quantity were hydrogen and helium, with trace amounts of lithium. That was it. Everything heavier, carbon, oxygen, nitrogen, iron, the calcium in bones, and the silicon in rock, none of it existed yet. The universe was chemically almost empty. The mechanism for building heavier elements had not yet switched on, because that mechanism is a star. Stars are the factories. They take hydrogen and helium and crush them together at temperatures measured in millions of degrees, fusing lighter nuclei into heavier ones, running through a sequence of reactions that builds the periodic table one element at a time. When a massive star exhausts its fuel and detonates as a supernova, it scatters everything it built back out into the surrounding gas. That gas, now seeded with heavier elements, eventually collapses again to form a new generation of stars, and those stars fuse still heavier elements, and so the cycle continues. Carbon, oxygen, and nitrogen are not products of the first generation. They require the cycle to have run at least once, Some of them require it to have run multiple times. Nitrogen specifically is what chemists call a secondary element. It is not produced directly from primordial hydrogen in a single round of stellar burning. It forms through a specific chain of reactions called the CNO cycle, and the inputs that chain needs, carbon and oxygen, are themselves products of earlier stellar generations. For nitrogen to show up in a galaxy's spectrum, that galaxy must have already produced carbon and oxygen in an earlier cohort of stars, watched those stars die, allowed the carbon and oxygen to disperse and mix back into the galactic gas, and then formed a second generation of stars that could use those elements as raw material for the CNO cycle. That is not one round of the factory running. That is at minimum 2. And each round takes time. How much time? Under conditions that astronomers consider normal for star-forming regions, a massive star, the kind that lives fast and dies in a supernova, burns through its fuel in a few million years. Call it 3 to 10 million years from formation to explosion. Then the ejector need to cool, mix with surrounding gas, and collapse into a new stellar generation. That cooling and mixing process takes additional tens of millions of years under typical conditions. Stack 2 generations together, and you are looking at a minimum of roughly 100 to 200 million years. And that estimate assumes the process ran at maximum possible efficiency with no delays. The Standard Model does not expect star formation in the early universe to have run at maximum efficiency. It expects the opposite. MOMZ14 existed 280 million years after the Big Bang. That is the total time available, the entire budget. And nested inside that 280 million years, the galaxy had to form its first stars from scratch, run those stars through their complete life cycles, disperse the products of stellar burning into surrounding gas, form a second generation of stars, run those through CNO burning to produce nitrogen, and do all of this at sufficient scale that nitrogen shows up clearly in a spectrum detectable from 13.5 billion light-years away. The margin is not tight. There is essentially no margin at all. The nitrogen case is the sharpest version of the problem, but it is not the only one. Across multiple JWST targets in the early universe, spectroscopic data is turning up elevated abundances of oxygen, carbon, and other elements that have no business being present at those epochs, if standard star formation timelines are correct. Each detection is its own version of the same paradox. The chemical clock says one thing. The cosmological clock says something incompatible. There are researchers who have proposed that the very first stars, population 3 stars, the hypothetical primordial generation that formed from pure hydrogen and helium, were vastly more massive than stars forming today, perhaps hundreds of times the mass of our Sun. Stars that massive would burn through their fuel in 1 million years or less and detonate with enormous force, scattering heavy elements across enormous volumes of space. If population 3 stars were that extreme, the first enrichment cycle could have run faster than standard models assume. It is a real hypothesis. It has adherents. But even under that accelerated scenario, fitting multiple enrichment cycles into 280 million years strains the arithmetic to its limits. Chemical enrichment does not happen in a single stellar generation. It requires multiple cycles of stellar birth, burning, death, and dispersal. And each cycle takes time that the early universe does not appear to have had. Running alongside the galaxy formation crisis is a separate but related problem. one that involves the state of the universe itself in its earliest surviving phase. To understand what JWST is finding here, you need a picture of what the early universe actually looked like before stars existed. For the first few 100 million years after the Big Bang, space was not empty in the way you might imagine it. It was filled with a thick fog of neutral hydrogen gas. Neutral hydrogen is opaque to ultraviolet light. That means the universe, during this period, was essentially dark and invisible, not just to telescopes, but in a fundamental physical sense. Light could not travel freely through it. No signal could cross the cosmos without being absorbed by the hydrogen fog sitting in its path. Then, gradually, something changed. The first stars ignited. The first galaxies switched on. Their ultraviolet radiation began pouring out into the surrounding gas, stripping electrons from hydrogen atoms and converting neutral hydrogen into ionized plasma. Ionized gas is transparent. As this process spread, slowly at first, then faster, patches of the universe began to clear. The fog lifted in expanding bubbles around the earliest bright sources. Eventually, those bubbles connected. The whole universe went transparent. This transition is called rionization, and it happened roughly 13.0 to 12.7 billion years ago, somewhere between 380 and 550 million years after the Big Bang. Rionization matters for a reason that goes beyond the mechanics of gas physics. It marks the moment the observable universe became observable. Before rionization, there was no way for light to carry information across intergalactic distances in a coherent way. After rionization, the universe was open, readable, in principle, by any instrument sensitive enough to detect ancient light. Every deep field image JWST has ever taken is only possible because rionization happened. It is the event that made the rest of the story visible. Before JWST launched, cosmologists had a reasonably confident model for how rionization unfolded. The dominant picture said the process was driven primarily by small, faint galaxies. The reasoning was straightforward. Bright, massive galaxies are rare. Faint, small galaxies vastly outnumber them. Even if each individual faint galaxy produced relatively modest amounts of ultraviolet radiation, their sheer numbers would add up. The total ionizing flux from millions of small systems would overwhelm the contribution from a handful of brilliant ones. Bright galaxies were expected to play only a minor supporting role, filling in around the edges. The faint majority was supposed to be doing the heavy lifting. What JWST is finding does not match that picture cleanly. Brighter and more massive galaxies appear to be contributing more ionizing radiation than the model predicted. Some regions of the data show unexpectedly high luminosity sources active at precisely the period when rionization was supposed to be driven by the faint population. Separately, the spatial structure of rionization itself appears patchier than models anticipated. Rather than a relatively uniform front of ionization spreading outward from evenly distributed small galaxies, the evidence suggests the process was more uneven, certain regions clearing far ahead of others, with the local density of bright sources playing a bigger role in determining where transparency arrived first. This patchiness has real consequences for how we interpret everything JWST sees in the rionization epoch. If some regions cleared early while others stayed neutral longer, then the sample of galaxies JWST can observe at those redshifts may be biased toward the already cleared zones. The galaxies inside neutral patches would be harder to detect, their light absorbed before it reaches us. Reconstructing a complete picture of how many galaxies existed and how they were distributed becomes considerably more complicated when the medium between them and us was not uniformly transparent. Then there is the specific case that has drawn the most attention. JWST identified a remarkably bright ancient galaxy active during the Rayonization epoch, bright enough to raise an immediate question about how much of the surrounding neutral gas it alone could have been responsible for clearing. A single source luminous enough to ionize a significant volume of intergalactic space is not what the faint galaxy-dominated model predicts. One bright galaxy does not overturn a cosmological model, but it raises the question of how many more like it were out there, and whether the standard census of ionizing sources was fundamentally undercounting the contribution from the high luminosity end of the galaxy population. Researchers who study rayonization have spent years building simulations that reproduce the timing and the topology of how the neutral universe became ionized. Those simulations were calibrated against the best pre-JWST data available. The new observations are not catastrophically inconsistent with every aspect of those simulations, but they are applying pressure in specific places, on the role of bright galaxies, on the uniformity of the process, on the timeline of when different regions cleared. Each pressure point individually might be absorbed with a targeted adjustment. The question, increasingly, is whether the adjustments needed in one place are compatible with the constraints coming from another. The picture of rayonization that is emerging from JWST data does not match the one drawn in advance, and explaining the difference is turning out to be harder than the researchers who designed the mission expected. To appreciate how disorienting these discoveries have been, you need a clear picture of what the models were actually supposed to deliver. Not vague impressions, not general expectations, specific, quantified, peer-reviewed predictions that were written down and published before JWST collected its first photon. This is important. When researchers say the data has broken the standard model, they are not speaking loosely. They mean the numbers coming back from the telescope do not match the numbers that were on paper before the telescope launched. The standard model, Lambda CDM, is not shy about making predictions. That is actually one of its strengths. Dark matter halos form first. Ordinary matter falls in. Gas cools slowly. Stars begin forming in small, irregular clumps. Those clumps merge over hundreds of millions of years, gradually assembling into larger structures. The model is precise enough to generate specific forecasts about what a telescope pointed at redshift Z greater than 10 should find. Small, faint, irregular proto-galaxies. Systems with very little stellar mass. No organized structure. No chemically enriched gas. The universe at 300 to 500 million years old, according to Lambda CDM, should look like the rough draft of something that has not yet figured out what it wants to be. That is what JWST was expected to confirm. Not because astronomers were being careless, because every observational test run before Webb launched had been consistent with that picture. Hubble had pushed as far as it could. The galaxies it found at extreme redshift were faint, small, and exactly where the model said they should be. Cosmologists had every reason to believe that JWST, pointing deeper, would see more of the same. Smaller, fainter, younger, the building blocks. Before launch, several groups published specific forecasts. The numbers varied slightly between teams, but the general consensus was clear. At redshifts above 10, you should not find galaxies with stellar masses exceeding roughly a few hundred million solar masses. Anything more massive than that would require star formation to have begun almost immediately after the Big Bang and to have proceeded at rates the model simply does not allow. Nobody put a massive, organized, chemically enriched galaxy in their predictions for that era. The model had no slot for it. Some researchers were cautious enough to note that JWST might find surprises at the extreme edges of the observable universe. Statistical flukes happen. The model has parameters with some flexibility. A handful of slightly anomalous objects would have been manageable. The standard response to one or two outliers is to check your photometry, revisit your redshift estimates, and see if there is a mundane explanation hiding in the noise. That is normal science. What nobody predicted was a consistent pattern across multiple independent teams, multiple separate fields, multiple instrument configurations, all returning objects that violated the expected ceiling on early galaxy mass. Not one anomaly, not two, a population. That is a different kind of problem entirely. The supermassive black hole findings had their own set of pre-launch predictions. Standard formation theory required billions of years of accretion to grow a black hole from a stellar remnant to the supermassive scale. Predictions published before JWST launched reflected this. Researchers expected that very early black holes, if detected at all, would be modest in size, the early seeds of what would eventually become the giants seen in later epochs. The idea that JWST would find black holes outpacing their host galaxies within the first few 100 million years after the Big Bang was not in the forecast. It was not even in the speculative end of the forecast. The chemical enrichment predictions followed the same logic. Heavy elements require stellar nucleosynthesis. Stellar nucleosynthesis requires time. Stars must form, burn, explode, and scatter their products before a second generation can incorporate them. The timelines built into Lambda CDM pushed chemically enriched systems well past the first billion years. Finding nitrogen, a secondary nucleosynthetic product, at 280 million years after the Big Bang was not a deviation from the prediction. It was off the chart the prediction was drawn on. What makes the gap between forecast and observation so uncomfortable is that it is precise. Researchers can go back to papers published in 2019 and 2020 and put the predicted numbers directly next to the observed numbers. The margin is not subtle. In several cases, observed galaxy masses exceeded predictions by an order of magnitude or more. That is not a calibration error. That is not a rounding issue. That is the model being wrong by a factor of 10, repeatedly, in the same direction, across independent measurements. The direction is always the same. The early universe was more advanced, more massive, and more organized than the equations said it should be. There is no natural reading of that pattern that leaves the standard model intact without significant modification. What was supposed to be a confirmation mission has turned into something the people who designed the telescope were not fully prepared for. By itself, any one of these findings might be argued away. A single massive galaxy at high redshift could be a calibration error. A single supermassive black hole forming too early could be a statistical outlier at the tail end of a distribution. One galaxy with no rotation. One galaxy with a bar structure it shouldn't have. One system of 5 merging galaxies at cosmic dawn. Any of those, standing alone, gets filed under needs follow-up, and the model moves on. Science handles anomalies all the time. That is not the situation here. What JWST has produced is not a single anomaly. It is a collection of independent findings from different research teams using different instruments, targeting different fields of sky, studying different physical properties, and arriving at different conclusions through different methods, all of which point in the same direction. Galaxies are too massive too early. They are too organized too early. They are too chemically enriched too early. The black holes inside them are too large for the galaxies that supposedly built them. The star formation efficiency is too high. The merger activity is too advanced. Every arrow, when you lay them out, points the same way. The early universe was doing more, faster, than the standard model says was possible. This is what distinguishes a crisis from a tension. In cosmology, a tension is when two measurements disagree by a few sigma, and the community suspects one of the instruments, or one of the underlying assumptions, is slightly off. Tensions get resolved. The Hubble tension was a tension for years before it hardened into something more uncomfortable. A crisis is when the disagreement is not between two measurements, but between the measurements and the framework itself, and the disagreement is large, consistent, and reproducible. What JWST is generating has moved, for a growing number of researchers, from the first category into the second. Not universally, the debate is real, but the direction of travel in the literature is visible. The specific parts of the standard model under the most stress are the ones that make predictions about how the early universe assembled itself. The timeline for galaxy mass buildup, the expected star formation rates in the first billion years, the mechanism by which supermassive black holes grow, the prediction that large organized structures should not appear until the universe is several billion years old. These are not peripheral features of the model. They sit near the center of what Lambda CDM was designed to explain. When Vera Rubin's rotation curves broke Newtonian gravity in the 1970s, the response was not to discard the model entirely, but to insert dark matter as a correction. The question now is whether corrections of that kind can still do the work, or whether the gap between prediction and observation is too systematic to patch. Other parts of the standard model remain solidly tested. The cosmic microwave background fits Lambda CDM predictions with extraordinary precision. The large-scale structure of the modern universe, the distribution of galaxy clusters and cosmic filaments matches the model well. Big Bang nucleosynthesis, the production of hydrogen and helium in the first minutes, is confirmed. These are not small checks. They represent some of the most precisely verified predictions in all of science, and nothing JWST has found disturbs them. The crisis, if that word applies, is localized to a specific domain. It concerns how the universe evolved during its first billion years, not whether the Big Bang happened, or whether the basic thermodynamics of the early plasma were correct. That distinction matters because it shapes what kind of solution might work. If the model were failing across the board, you would need to discard it entirely. What is happening instead is more surgical. The framework is failing in a specific era, at specific scales, in specific ways that all rhyme with each other. That is actually useful information. It suggests the standard model is not wrong so much as incomplete, missing something that operated with unusual intensity in the young universe and has since faded or changed. What that something is, nobody has agreed on yet. The community's position right now is uncomfortable in the specific way that scientific communities get uncomfortable when they can see a problem clearly but cannot see the solution yet. Papers are being published that 5 years ago would have been considered too radical for serious journals. Phrases like challenges the standard model and requires new physics have migrated from the fringes into the mainstream literature. Researchers who spent careers building Lambda CDM are being careful with their language in interviews in a way that itself signals something. The model is not being abandoned. It is being watched very closely by people who built it and are no longer fully confident in it. The pattern of anomalies is what keeps astronomers up at night, not any single result, but the shape of all of them together, pointing consistently in the same direction. When the standard picture starts developing cracks this wide, people begin looking more seriously at the alternatives. The most prominent of those alternatives has been around since 1983. Modified Newtonian dynamics, known as MOND, was proposed by Israeli physicist Mordechai Milgram. The core idea is simple enough to state in one sentence. Gravity does not behave exactly the way Newton and Einstein described it, particularly in environments where gravitational acceleration drops very low. At ordinary accelerations, the kind you experience on Earth or in our solar system, MOND and standard gravity give essentially identical predictions. You would never notice the difference. But in the extreme outskirts of galaxies, where gravitational pull becomes extraordinarily weak, MOND says the rules change. Gravity holds on a little harder than it should. This sounds like a small tweak. The consequences are not small. For decades, the main reason astronomers cared about MOND at all was the rotation curve problem. Galaxies rotate, and when you measure how fast stars orbit at different distances from the center, the outer stars move far too quickly for the visible mass to explain. Standard physics says they should be moving slowly, nearly escaping. Instead, they hold their orbits as if something invisible is pulling them in. The standard model's answer is dark matter, an enormous invisible halo surrounding each galaxy, providing the extra gravitational grip. MOND's answer is that you don't need invisible matter at all. You just need gravity to behave differently at low accelerations. For individual galaxy rotation curves, MOND works remarkably well, often better than dark matter models that require careful tuning of the halo structure. But MOND has problems, serious ones. The cosmic microwave background, the fossilized radiation left over from 380,000 years after the Big Bang, is one of the most precisely measured datasets in all of science. Its pattern of tiny fluctuations is exquisitely well explained by a universe full of cold, dark matter. MOND does not naturally produce that pattern. Galaxy clusters are another problem. When you measure the mass of galaxy clusters through gravitational lensing, the visible matter alone still falls short, even after MOND's modification. There appears to be something extra there regardless. Most cosmologists pointed to these failures and concluded the case was closed. MOND explained one thing well and everything else poorly. It was filed under interesting but wrong. Then JWST started returning data. Stacey McGaw at Case Western Reserve University, one of the few mainstream researchers who had continued taking MOND seriously, pointed out that the early massive galaxies JWST was finding aligned more naturally with what MOND would predict than with what dark matter models forecast. In a universe governed by MOND, matter collapses under its own gravity more efficiently, without waiting for dark matter halos to assemble first. Structure forms faster. Galaxies get massive earlier. The impossibly early galaxy problem is, in a MOND framework, considerably less impossible. McGaw and colleagues ran the numbers and found that the JWST galaxy population at high redshift looked roughly like what MOND-based simulations had been predicting for years, while the rest of the field was predicting something else entirely. This has not converted the cosmological community. MOND's failures with the CMB and cluster lensing remain real and unresolved. No version of MOND yet proposed handles all of the observational evidence coherently. But the conversation has shifted. Researchers who would not have engaged seriously with the theory 5 years ago are now at least acknowledging that it predicted something correctly that the standard model got wrong. That is not nothing in science. MOND is not the only framework getting attention. Early dark energy is another proposal. The idea that a brief burst of additional energy density in the universe's first few 100,000 years could have accelerated early structure formation and might also help resolve the Hubble tension. The problem is that early dark energy models that fix one discrepancy tend to create new ones elsewhere in the data. They are patch solutions, and patches have a way of tearing at the edges. Interacting dark matter is another direction, proposing that dark matter particles interact with each other or with ordinary matter in ways beyond simple gravity, potentially allowing structures to assemble faster than the standard cold dark matter picture allows. And primordial black holes have come back into serious discussion as potential seeds for the supermassive black holes JWST is finding so implausibly early. If black holes of significant mass form directly from density fluctuations in the first fractions of a second after the Big Bang, before any stars existed at all, the growth timeline becomes far less impossible. Each of these proposals has a community of researchers developing it, running simulations, testing it against the growing JWST dataset. What separates a speculative alternative from an accepted theory is a specific kind of pressure. The alternative has to predict something that hasn't been measured yet. Then that measurement has to come back in its favor. Explaining existing anomalies after the fact is necessary but not sufficient. The frameworks now competing for attention are at different stages of making those forward predictions. JWST still has years of operations ahead in which those predictions could be tested. None of the alternatives are clearly winning. What is clear is that the discomfort with the standard model has reached the point where frameworks that used to be dismissed outright are now getting a serious second hearing. The easiest way to misread this situation is to conclude that cosmology is in freefall, that everything physicists thought they knew has collapsed. That is not what is happening. But what is happening is also not what the more defensive voices in the field would have you believe. That is, that a few adjustments to existing parameters will smooth everything over and the model will emerge intact. The scientific community is genuinely divided. That division runs deeper than it has at any point since the standard model was assembled in the late 1990s. The researchers who study early galaxy formation are not speaking the way they spoke 5 years ago. The language has shifted. Papers that would have hedged carefully in 2020 are now using words like tension, crisis, and in some cases, fundamental incompatibility. That change in vocabulary is not accidental. There are researchers who remain confident. They will tell you that Lambda CDM has survived serious challenges before. The model absorbed the discovery of dark energy in 1998. That required adding an entirely new and poorly understood component to the universe, and it survived. It absorbed early discrepancies in large-scale structure surveys. It has a long track record of bending without breaking. Their position is that the anomalies from JWST are real, but that they reflect incomplete modeling on the galaxy formation side, rather than errors in the underlying cosmology. In this view, the physics of star formation feedback, gas dynamics inside early galaxies. The behavior of dark matter halos at small scales are not fully understood. The discrepancies between prediction and observation are gaps in those submodels, not cracks in the foundation. This is a defensible position. It is not unreasonable, but the researchers who are more alarmed would point out that this argument has a specific problem. You cannot indefinitely absorb anomalies by attributing them to uncertain submodels without eventually having to demonstrate that those submodels can actually be fixed to match the data. And in some cases, the required fixes are not small. Getting early galaxies to form with near total star formation efficiency using known feedback physics is not a matter of tuning a parameter. The feedback mechanisms that prevent runaway star formation in the modern universe are well studied. Turning them off or inverting them in the early universe is not a minor adjustment. It requires a different regime of physics, and that is a harder claim. The distinction worth holding onto is between two very different kinds of model revision. The first kind leaves the framework standing and adjusts the numbers inside it. More efficient cooling in early halos, different initial conditions for dark matter clustering, revised assumptions about the timing of Rayonization. This kind of adjustment is normal science. It happens after every major observational advance. The second kind of revision requires that the framework itself be rebuilt. This was because the new observations are not compatible with the structure of the theory, not just with the specific values it uses. The concern among the more alarmed researchers is that some of what JWST is finding falls into that second category. The sociology of how science moves through this kind of moment is worth understanding. Paradigm shifts in physics do not happen cleanly or quickly. The anomalies in Mercury's orbital precession that Newtonian gravity could not explain were documented for decades before general relativity arrived to resolve them. The ultraviolet catastrophe in classical physics sat unresolved for years before quantum mechanics provided a new foundation. In both cases, the anomalies were real and documented well before anyone had a replacement framework. The community spent those intervening years in a state of acknowledged discomfort, publishing papers about patches and workarounds, running debates at conferences, gradually accepting that something foundational had to change. That process is slow. Communities of scientists have careers and reputations and institutional commitments built around existing frameworks. The shift from anomaly to accepted crisis to new paradigm is measured in decades, not months. The language in JWST-related papers and interviews has been moving along that arc in real time. Researchers who were cautious in 2022 are more direct now. The phrase "impossibly early galaxies" moved from informal shorthand to appearing in peer-reviewed abstracts. Phrases like "challenges to Lambda CDM" and "in tension with standard model predictions" are appearing in paper titles that 5 years ago would have buried those claims in the discussion section. That is a measurable cultural shift in how the field is talking about what it is seeing. What nobody responsible is saying is that the observations are wrong. The data has been independently verified across multiple instruments, multiple teams, and multiple fields of early universe research. The question is not whether the anomalies exist. The question is what they mean and how deep the reckoning will have to go. Some researchers think the answer is a patched and extended lambda CDM that survives in modified form. Others think the answer will require something that does not yet have a name. The more honest description is that the model is under stress in specific and documented places, that certain predictions have failed badly enough to require something more than minor adjustments, that nobody yet has a fully worked out replacement ready to take their place. What JWST is doing to cosmology is not unprecedented in the history of physics. It has happened before, more than once, and each time the pattern looked roughly the same. Observations accumulated that didn't fit. Researchers tried to make them fit anyway. The adjustments grew more awkward with each attempt. And then, eventually, someone arrived with a framework that explained both the old data and the new anomalies at once, and the field moved forward. The question JWST is forcing right now is whether we are in the middle of that process or still at the beginning of it. Consider what happened with Mercury. For decades in the 1800s, astronomers tracking the planet's orbit noticed a small but persistent discrepancy. The point at which Mercury swings closest to the Sun, its perihelion, was shifting slightly more than Newtonian gravity predicted it should. The gap was tiny, around 43 arc-seconds per century, a number so small it sounds trivial. But Newtonian mechanics was precise enough that even a small discrepancy was a real problem. Theorists tried to explain it away with an undiscovered planet, with atmospheric drag, with measurement error. None of those explanations held. The anomaly sat there for nearly 50 years, unresolved, until general relativity arrived and accounted for it exactly. The model didn't need a patch. It needed a replacement. The photoelectric effect tells a similar story. Classical wave theory described light as a continuous wave, and it worked beautifully for most purposes. Then experimenters noticed that when light hit a metal surface, it ejected electrons in a way that wave theory simply couldn't explain. The energy of the ejected electrons depended on the frequency of the light, not its intensity. That made no sense if light was a wave. Einstein solved it in 1905 by treating light as discrete packets of energy, photons, and the photoelectric effect snapped into focus. Classical theory wasn't wrong about everything. It was wrong about this specific thing, and fixing it required thinking about the nature of light in an entirely different way. Those are the models JWST's situation gets compared to most often, and the comparison is fair. The anomalies emerging from Webb's data are not sitting at the edges of what the instruments can detect. They are in the center of the measurements, confirmed by multiple teams, and they are pointing at something the lambda cold dark matter model was not built to accommodate. The question is, which part of that model breaks first? There are a few candidates. Dark matter is the obvious one. Lambda CDM depends on cold dark matter as the gravitational scaffolding around which galaxies form. If dark matter doesn't behave the way the model assumes, if it interacts differently, clumps differently, or has properties that change over cosmic time, the entire timeline for galaxy formation could shift. Galaxies could assemble faster. Structures could emerge earlier. Some of what JWST is finding might follow directly from that. But modifying dark matter enough to explain the early galaxy problem tends to break other things the model currently gets right, which is the basic trap every proposed fix runs into. Dark energy is another candidate. The Lambda CDM model treats dark energy as a cosmological constant, a fixed energy density built into the fabric of space that drives accelerated expansion at a steady rate. The Hubble tension, the confirmed discrepancy between early and late universe expansion measurements, suggests this might not be right. If dark energy varied over time, the expansion history of the universe would differ from what the standard model predicts. That could affect when and how structures form. Early dark energy proposals try to address this by adding a brief burst of additional energy density in the early universe, which would modify the expansion rate just enough to bring the Hubble tension measurements into agreement. Whether it would also explain the galaxy formation anomalies is less clear. The deepest possibility is that general relativity itself is incomplete at cosmological scales. Einstein's equations have been tested extensively within our solar system and across relatively nearby galactic scales, and they pass every test. But applying them to the universe as a whole, across 13.8 billion years of expansion and structure formation, is an extrapolation of enormous scope. It is at least conceivable that gravity behaves differently at the largest scales or across the longest timescales in ways that haven't yet been detectable except in a telescope with Webb's reach. This is essentially what MOND and its relativistic successors are claiming. Most cosmologists remain skeptical, but skepticism has softened because the standard framework keeps failing to explain what the data is showing. What none of these options have in common is a single worked-out framework that handles all the anomalies at once. There is no general relativity waiting in a drawer somewhere, ready to be presented. There are competing proposals, revised parameters, exploratory theories, and a great deal of careful debate about which anomalies are most constraining and which might dissolve under closer scrutiny. That is exactly where physics sits when it is between frameworks. Too many problems for the old model, not enough consensus around any replacement. The thing about a genuine paradigm shift in physics is that it tends to look, from the inside, exactly like what is happening right now. A pile of anomalies, competing explanations, and a growing sense that the framework needs more than a patch. There is a strange additional layer to all of this that is easy to overlook when you are reading about specific galaxies and specific distances. Every number JWST produces comes wrapped in a fact most people absorb once and then stop thinking about. Light travels fast, but the universe is large enough that speed does not help much. When the telescope locks onto a galaxy at redshift z equals 14, it is collecting photons that left their source 13.5 billion years ago. The galaxy that emitted that light does not look like that anymore. It may not exist at all. This is not a minor philosophical footnote. It changes what the word found actually means. When a headline says JWST found a galaxy from 280 million years after the Big Bang, what it means precisely is that JWST intercepted light that was emitted 13.5 billion years ago by an object that was, at that moment, 280 million years old. The object itself has had 13.5 billion years to evolve, merge with other galaxies, exhaust its gas, collapse, or transform into something unrecognizable. We have no image of what it looks like today. We have a photograph of what it looked like then, and we are trying to reconstruct the rules of physics from it. Think about what that requires. You are handed a single frame from a film. The frame shows something unexpected. You need to determine whether the entire film violates the laws of storytelling, or whether you are just missing context. That is roughly the epistemological situation astronomers are working in every time JWST returns data from the deep field. The image is real. The light is real. What you can conclude from it involves considerably more inference than the headlines tend to convey. The distance problem adds another layer of uncertainty that does not get enough attention. The distances assigned to these early galaxies are not measured directly. You cannot send a probe. You cannot bounce a signal and time the return. What astronomers measure is redshift, the stretching of light toward longer wavelengths caused by the expansion of space between the source and the observer. A galaxy at Z equals 14 has had its light stretched by a factor of 15 since it was emitted. That redshift measurement itself is precise. What converts redshift into an actual distance, though, is a model. Specifically, it is the lambda CDM cosmological model, with its particular values for the expansion rate of the universe, the density of dark matter, and the behavior of dark energy. Those are the parameters that tell you how far away something at a given redshift actually sits. Here is where the Hubble tension re-enters the picture. If the expansion rate of the universe is genuinely uncertain, if the two methods of measuring it give irreconcilably different answers, then the distances derived from redshift are also uncertain at some level. Not wildly wrong, but uncertain enough to matter when you are making claims about whether a galaxy at 280 million years post-Big Bang is too massive to exist. The mass estimates depend on the luminosity. The luminosity depends on the distance. The distance depends on the expansion model. The expansion model is currently contested. Each link in that chain carries error bars, and those error bars compound. None of this means the anomalies are illusory. Multiple independent teams using different methods have confirmed the most dramatic findings. The impossibly early galaxies are not going away on a calibration fix. The enrichment signatures in MOM-Z14 are spectroscopic. They are in the specific wavelengths absorbed by nitrogen atoms, and that is not something you misread. The crisis is real, but the precision with which anyone can claim to know exactly how massive a galaxy from 13.5 billion years ago actually was carries legitimate uncertainty that sometimes gets lost between the discovery and the press release. What is genuinely established is the direction of the anomalies. Across dozens of targets, confirmed by independent teams, galaxies in the early universe are consistently more luminous, more massive, more chemically evolved, and more structurally organized than any pre-launch prediction. The specific numbers attached to any single galaxy may carry uncertainty. The pattern does not. That pattern is what physicists are trying to explain, and the honest position right now is that no existing framework explains it cleanly. What is genuinely unknown is almost everything about what those galaxies look like today. We have no access to the present state universe at cosmological distances. We see deep time, not current time. Everything JWST observes is a record of what was, filtered through 13.5 billion years of travel, interpreted through models that are themselves under stress. Every image JWST sends back is a message from a universe that no longer exists in that form. And what we are actually learning from those messages is a question astronomers are still actively working out. Step back from the individual discoveries, and the picture that emerges is both simple and vertiginous. A telescope was built to confirm a model. The model had survived every observational test for 25 years. It had predicted things accurately enough that the people who built it were confident in what Webb would find. And then Webb found something else. Not at the edges of the data, not in marginal cases that could be argued away over coffee. The anomalies showed up in the middle of the fields, confirmed by multiple teams, in multiple independent categories, all pointing in the same direction. Galaxies too massive, black holes too large, structures too organized, chemistry too advanced. The model that was supposed to be validated is now the model under the most sustained observation or pressure in a generation. There is something genuinely strange about living through a moment like this in science. Most of physics is not in crisis. The laws governing how matter behaves, how light travels, how energy moves through systems, these are tested constantly and they hold. What is cracking is something more specific. The story cosmologists had assembled about how the universe went from featureless plasma to the structured world of galaxies and clusters we inhabit now. That story was detailed and mathematically precise. It made specific, testable predictions about what the young universe should look like. Webb looked. The predictions were wrong, not by small margins, but by amounts that are difficult to absorb without confronting the possibility that something fundamental is missing from the framework. What happens next is not a collapse, it is a reckoning. New observatories are being planned. Theoretical physicists are stress testing alternatives that a decade ago would not have survived the first conference presentation. Dark matter models are being re-examined. The behavior of gravity at cosmological scales is being questioned with a seriousness that would have seemed fringe 5 years ago. The data from Webb is still accumulating. Each new observing cycle pushes the redshift frontier a little further, places a few more objects in the category of things the standard model cannot explain. The database of anomalies is growing faster than the theoretical frameworks designed to contain them. This is not a failure of science. A model producing predictions that observations contradict is not a sign that the enterprise is broken. It is the most productive thing that can happen to a scientific field. The anomalies are the information. The discomfort in the research community is evidence that the process is working. History says the next framework will not simply patch the existing model. It will explain everything the current model explains, and it will also explain the things Webb is finding that the current model cannot touch. That framework does not exist yet. Nobody has written it down in a form that survives contact with all the data. The universe Webb is showing us is not the one we thought we understood, and what we do with that is the most interesting question in physics. Right now,